And so Daniel is a postdoc here at the Martinos Center, working with me and Laura Lewis, also a former student of David Norris, we heard from yesterday, and Jose, we heard about a lot. Daniel's been doing a lot of methods development for fMRI, also a lot of work on fast fMRI, and especially looking into cortical segmentation. We want to learning about this from Daniel. Thanks so much.
All right. Thank you. Can everyone hear me okay? Also online, I don't see the Zoom, but yeah, everything's okay. Okay, so the agenda of today is we'll talk a little bit about the goal of cortical segmentation. Can you guys hear me okay? No, this is not a good idea. It's going to slide down.
Pinch your shirt.
Okay, is this better? Okay, thank you guys. Yeah, I'll talk about the goal of cortical segmentation, the recipe, how do we perform it automatically. And here I'll talk about all the steps that are involved in doing the cortical segmentation. I'll talk about FreeSurfer as a benchmark. Just a word, FreeSurfer is the canonical tool for cortical segmentation in our field. Many people don't know, but all the tools that are used for the Human Connectome project, for example, are based off of FreeSurfer. And most papers that talk about cortical segmentation usually use a comparison against FreeSurfer to see how they're performing. That's why we're going to use it. I imagine many people have experience with it, or if not, we can talk about it later. Reasons that make the segmentation challenging at high field and measures to guide FreeSurfer and to give us a workable solution. If we have time, I'll talk about a segmentation challenge and how do we think about it as we're trying to solve it with automatic tools. An example fMRI study, how do we validate that this segmentation is working accurately, or how do we visualize it? And again, if there's time, some commands that we can use from FreeSurfer to do cortical layering and generate volumes and additional surfaces. So the goal. I took this from a paper from Jose and David, where they mentioned that if we consider laminar fMRI, the challenge is really to distinguish these layers of unequal thicknesses that are found in the neocortex, which itself is very small. So if we look at that image that we've seen yesterday in a couple of talks and we place it here in our layers, we see that it's really tricky to get this accuracy across the whole brain. Here I'm showing a picture overlaying the calcarine sulcus of a layering that was done with FreeSurfer automatically. And the goal is either to get something that looks like this across the whole brain or in a region of interest, or to get a map of cortical depth where you know how far a voxel is from either the white or the peel surface. So this is what we're going to try to achieve step by step. And we want to do this automatically for a couple of reasons. The first is that automatic segmentation is objective. We use predefined algorithms in the data, and the outcome does not depend on our subjective experience. It is reproducible. As long as we have the same data set and the same parameters, we can give it to anyone. We can produce it across different subjects, and it should always work the same way. And it is efficient, right? It saves us a lot of time. Manual segmentation is a laborer's work. And so if we're not doing that, we can do other things, and that's good. I should also mention that for low fields, automatic segmentation is a solved problem. If you take a MP-RAGE image, as FreeSurfer suggests you to use, and run it through their algorithm, 10 out of 10 times it's going to work. You may have an issue or the other, but it's really a solved problem. And things break down when we move to 7T, and you've seen this in Saskia's talk yesterday. As we move from 3.3 to 7T, there are many things that happen to our image. First one that really jumps to the eye is that this inhomogeneity of the signal, right? When we look at the 7T, which is what we call a bias field, is very strong. There's also this strong presence of the arterial signal, inflow weighting that we see here in these images that is not really present at 3T. And beyond that, there's other different distortions. There's other problems that we're dealing with. There's more variation in the signal intensity across the brain. It makes it really tricky to segment. So if we just run it through FreeSurfer, if we take a 7T data set and run it through FreeSurfer, we see that it doesn't really work. There are many things that have to be solved first. But if we do a little bit of fine tuning, I'll just note that these are different slices, even though they're from the same subject, but we can really get it to work to very satisfactory levels. So this is what we'll talk about today. And this is a slide that I took from Renzo, where he mentioned what are the challenges of doing things at 7T. And gray matter segmentation with layer accuracy is really hard. The title of this talk is automatic, but we'll be talking about fine-tuning and how we drive it. It's still some manual work. At the end, we have the manual work of getting the data and the algorithm right, and the automatic part is just letting it do the surface placement for us. But there's still some manual work that we have to do here, just to make that clear. So what is the recipe, or a recipe with FreeSurfer? These are the methods of FreeSurfer's command for cortical segmentation, recon all. There's a lot going on there. There's 4 steps. They're the fundamental steps that I would like to talk about. First one is here the removal of non-brain tissue, which is essentially brain extraction. So I'll talk about why is that important. Intensity normalization, which is correcting for that bias and putting values in a scale that FreeSurfer knows how to deal with. Tessellation of the gray matter, which is the generation or the initial placement of the surfaces. And then a surface deformation following intensity gradients to optimally place it with a precision that is higher than our Vox image. And there's about 100 commands under the hood. Of course, we can't talk about them all. More than 20 methods papers written about it. The cool thing is that it's still in active development. And I think even if we were to use other tools, knowing how FreeSurfer works, many of these ideas will transfer to other tools as well. The cool thing here is that there's an active mailing list and lots of experts. And if you have a question, it's very likely that someone can help you with it. So the recipe is as follows. We started our data, we normalize an image so that the intensity looks more or less the same. We extract the brain, we segment the white matter, and then we initialize, fix, and place the surfaces where we want them to be. Recon all script does all of this for you. So it does all from the bias field correction all the way to the end. For 7C, the only addition that we do, or the way we modify it, is we change the bias field correction for SPM because it really works better. And I'll show you why as we jump to each of these steps. So for the bias field correction, without any bias field correction, we have this extreme variation of signal intensity across the image. And since the segmentation wants to identify what are the intensity values that belong to white matter and gray matter, if there's any other change in these intensity values across the brain, and it's going to be really hard for us to know what these tissues are. And if we look at this image here, we can see, for example, that the gray matter or that the white matter here in the front of the brain has a value that is much lower than the gray matter in the back of the brain. So there's no way for us to segment this globally if this intensity is changing everywhere, if we don't have any other priors for this. If we do the default bias field correction, which works great for 3T, it's still not really sufficient to clear up the entire brain. That's why we use the SPM one, which has proven to be more robust. And I think you can appreciate, especially here at the cerebellum and at the skull, how we can get a much better homogenization of the signal. So we give this as an input to FreeSurfer. The bias field correction has 2 hyperparameters, and this is a practical course, so I just want to bring it up. There's a regularization factor and a bias full width half max. And these parameters really affect where the surface will end up being placed. So this is generated from the same data, but pre-processing with different SPM hyperparameters. Knowing what works best should be a matter of empirical exploration. This is even in the SPM manual. Here just showing a little bit the 2 parameters that we can control and how they impact the different data, right? So we can tune with them. I noticed that for the data that I collected here, the Martinos, with the protocols that we have been using, these values seems to have worked the best. And the trade-off is always the same, is should we assign the contrast that we're seeing of this change in signal intensity to actual tissue contrast, or should we assign it to the bias? And if we imagine that the thickness of the cortex is very small, if we don't have much contrast between gray and white matter, and depending on how we regularize this or how large the bias field is varying, the algorithm could assume that that very small contrast between white and gray is actually due to a bias and end up removing it, flattening that contrast. And that's why it's important to tweak these parameters and to know more or less, if we have an idea of what this bias field looks like, how we can control it. So moving on to brain extraction. Why is it even important to extract the brain? And the point is that if we don't extract the brain and we're just looking at all the values across the brain, then everything else that is non-brain is changing the distribution of signal intensities. So if we want to say that the signal comes from 3 classes, which are CSF, white matter, and gray matter, if we have this co-presence, then that's not truly the case. That's why brain extraction is important. And here's just a distribution or the histogram of these two images. And we see how we can kind of identify different classes here, potentially the white matter and maybe a distribution of gray matter, if we know what to look. Here in this case, it's much more complicated, right? I mean, it's potentially still doable, but it's much harder for an algorithm to interpret these data sets. The brain extraction can fail. Sometimes default settings are too conservative, so they include a little bit more of the sagittal sinus, or they may include also parts of the skull, depending on how we're doing it. And there are some parameters that we can pass to FreeSurfer through this expert file that will modify this brain extraction, so we can change it. FreeSurfer is moving to AI methods to do this, and they work very well. So maybe this is not something that we should worry about anymore. But it's good to know that all of these parameters can be tuned and modified. And if you see that that's failing, maybe you can intervene early, and then the rest of the pipeline goes on smoothly. Next step is segmenting the white matter. It's where the first initial surfaces will be generated from. The difficulty here is that, in particular at 70, that the mean intensity of gray matter is changing all across the brain. And so we're setting these thresholds where we want to set the surface, or where we segment it, will also vary across the brain. If we have a threshold that works well for segmenting white matter. Back on.
Yeah, it's just a little flaky back now.
Okay. Okay.
Your left side. Oh, yeah, it's a great idea, Kevin. Yeah, because you keep turning it.
Is this okay? Okay. So an issue with the segmentation is that it may end up including more or less white matter, depending on where we are. So we can actually tune these parameters in the MRI segment. We can change these parameters gray low, gray high, and white matter low, which may be useful for our 70 data to tweak how the segmentation is performed. Finally, generating and fixing the surfaces. I included all of this in a single block because we want everything to work. And when we get to the stage, the surfaces should be placed by themselves. The thing is that the surface placement, the last step that FreeSurfer does, depends on the image intensity gradients across the surface. So even though it initializes with that segmentation, it optimally places the surfaces based on its estimates of the class distributions. What are the values of white matter? What are the values of gray matter? And what do we expect? Where do we expect that border to be? And so we can push those surfaces around, as we're seeing here. There's some parameters that we can tune that can really move things around. And so it's not that FreeSurfer will always fail. It will fail if it's doing something to a data set that's different than what it is expecting. If we tune these two together, we can get it to work actually pretty well. So all those effects of bias fields, the normalization, right, parameter fine-tuning, brain extraction, end up affecting this class statistics and end up influencing, even if indirectly, the placement of the surfaces. This is also something that we can control. Maybe it's upstairs. Okay. The commands that controls this placement is called MRIS auto.gwstat. And what it generates is this class statistics where it tells you what are the values that it found, the average values in the PO border, inside, outside, and it has some surface placement thresholds of what it considers where these surfaces should actually be. And it will use these values to then optimally place the surfaces. These are values that we can play with. Of course, they're very sensitive, but once they're fine-tuned to a particular acquisition method that we have, then it's likely that they'll also work for other subjects acquired in the same way. We can change and control these parameters. More information, if you just look up the command, you can see everything that can be tuned. And again, seeing here a little bigger the effects that this can have on the placement of the surfaces. So now I'll talk a little bit about how do we think about a segmentation challenge. And a big segmentation challenge that we have is usually this isocontrast between the sagittal sinus and the dura mater. And then we see that the PO surface ends up including the sagittal sinus. And the question here is, okay, what went wrong and how do we fix this? Where do we even start to look, right? And we can see where's the problem. Is the data the problem? We should have acquired maybe a data set that actually has a better contrast here so that this wouldn't happen. Is it the pre-processing? Did the bias field actually remove whatever contrast was present between these two, making the contrast even smaller? Is it the free surfer parameters that we choose for the placement of the surfaces? Limitations of the algorithm? There are many things that we could have tweaked here to maybe try and solve this problem. But if I were to look at this and say, well, maybe the easiest thing here is to actually fix the co-stripping or the brain extraction. Because if we look at the mask, it includes the sagittal sinus. Maybe that's the way we want it to be, but this would be a place where we could easily modify that mask, excluding the sagittal sinus from the mask, and rerunning free surfer would then not allow these surfaces to be placed outside of what's the brain. So if we fix this early, for example, then we don't have to deal with anything else. It'll trickle down to the exact positioning that we want the surfaces to be. And finally, since we still have a couple of minutes, I'll show an example fMRI study and how do we look to see that these surfaces are actually okay. This is a study of the visual field. 16 slices placed over the calcarine sulcus, gradient echo API. It's an fMRI study with visual stimulation. How do we automatically segment the gray matter here and check that the results are okay? There's not much contrast in the image. Maybe there's a little bit, but it would be very tricky to do this in API space. And so the strategy is we use the anatomical. We assume that it is registered. We'll hear more about this later. And we use free surfer to generate the surfaces. So if we do this, and this is what it looks like, we can maybe, look here and judge, does this work? Is this okay? Are the surfaces well positioned? But it's still hard to judge. And so an idea that we've been exploring here at the Martinos is acquiring an auxiliary data set of a T1 weighted API image that has a better contrast and the same resolutions and distortions. And then when we overlay that, we can then easily identify if there's any errors in our segmentation and if it's working well. And because we know that this is distortion matched with our API and it's easy to co-register both of them, then if things look okay here, it's safe to assume that it will also be in the correct position in our native space. Finally, some free surfer commands for cortical layering, assuming that this is all done, and then we want to extract our cortical profiles. One command that's very useful, it's called MRIS expand. This flag thickness just makes it such that we expand it as a function of cortical depth. So here, if I set it to 0.5, it'll generate an intermediate layer between the pure and the white, right at a cortical depth that corresponds to half of the thickness. Once we have those different layers, we can pass this in inputs to this command called MRIS fill, which will generate a volume with everything that is inside of that surface. And then just by playing by subtraction and addition of these different volumes, we can then generate ribbons in volume space with whatever thickness we want. We can combine these volumes and generate volumes with layers that are identified or compartments that are identified by different indices and automatically generate the ribbon volume. So as concluding remarks, the best segmentation is the one that we can get to work. We can stay focused even though these methods require the whole brain to work. And I think this is an important point as well. As we're acquiring our MP range, free surfer is using the whole brain to place those surfaces and compute those statistics. So even if we're interested to get those surfaces to work only in V1 or in M1, we should always consider that the data has to be okay across the whole brain. Many automatic methods require whole brains, so it's nice to optimize overall. Fine-tuning works really well. We can get this to work. Maybe we can talk to the free surfer team to, do some calibration for us, and so that it just works even easier. Every step counts. It's nice to debug problems before, see that the data has the contrast that we want, and then tune from there. And we can try different tools and see how the results compare. As Renzo pointed out in his comics, it's not a trivial problem to solve, but it is solvable. Everyone does it slightly different. I hope that some of these tools can help you find your own solution as well. And there's this interaction, right? Data set and algorithm. It's nice to think of both together when we're doing these problems. Finally, on the importance of fine-tuning, these are two papers from, the first paper is a citation from Free Surfer as well, where they talk about it's hard to do things without manual intervention. And I think Farouk will talk more about that. Some cases are just so special that maybe just doing things automatically is not the way to go. And also other package developers have already pointed out that when you're trying to do this segmentation, the authors usually do look at these images and go through this fine-tuning. So all the tools that looked automatic today, the solved problem of free surfer at 3 Tesla, the authors put a lot of time in actually making that work before it became automatic for us. And maybe we're at the stage that we're doing this now so that by the next workshop, things will be automatic for people doing laminar fMRI. With that, I'd like to thank everyone. I'd also like to thank my PI, Laura Lewis. Her name is not here, but she also helped me a lot here. And special thanks to Divya, Anna, John, Doug, who I've had some discussions with as well, and the Free Surfer team.